Working in hazardous environments requires absolute precision in tracking invisible threats. Managing this risk relies on three distinct fields of knowledge. We must quantify raw exposure in the air, determine exact biological limits for the human body, and deploy specific physical detection mechanisms. Without mastering all three of these pillars simultaneously, establishing a functional baseline for radiological safety is impossible. To understand the threat, we have to distinguish between raw radiation in the environment and the risk it actually poses. We measure raw exposure in the air using Rontgens, while we measure the total energy actually absorbed by matter in RADS or Grays. For example, an exposure of 1 Rontgen translates directly to an energy absorption of 98 ergs when interacting with human soft tissue. To calculate the actual physiological damage, we rely on a final critical metric, biological risk, measured in REMS or sieverts. This factors in the specific radiation hitting the body. Pure exposure data lacks the context needed to predict survival. Managing risk requires calculating the sievert. For natural background radiation, the average allowed dosage is strictly 100 millirem per year. Looking at the top rows, the clinical tipping point begins at 20 rem, observing possible chromosomal damage and reduced white blood cells. The danger scales rapidly. Mild sickness occurs between 100 and 200 rem. Above 400 rem, exposure leads to acute illness and early death. This table compares legal occupational limits. Industrial workers are permitted significantly higher exposure thresholds than the general public, which is particularly visible in the allowances for hands and legs. Because physiological failures scale aggressively, elevated industrial thresholds mandate specialized protective measures and constant active monitoring. We cannot see these radioactive threats directly. Instruments must measure its physical interaction with specific matter to convert events into readable electronic data. This diagram shows a standard gas-filled detector setup. On the right, we see how a common household smoke detector uses an ionization chamber, triggering an alarm when smoke particles interrupt the internal electrical current. This schematic details a Geiger-Müller counter. It upgrades the basic gas-filled concept by utilizing high voltage and halogen gas to multiply the internal signal, allowing it to track alpha, beta, and gamma particles. Alternatively, this diagram illustrates a scintillation detector. It relies on radiation hitting phosphor materials to generate measurable flashes of light, which bounce through the photomultiplier tube shown here. For high accuracy, semiconductor detectors offer a solid-state alternative. They work by tracking electron void pairs inside materials like germanium when interacting with radiation. Neutrons present a unique complication because they lack an electrical charge. Detectors must track the secondary alpha particles created when neutrons react with target elements like boron-10. Successful detection requires matching the right physical reaction to the specific radiation you attempt to find. You cannot manage a hazard that you cannot accurately measure. The everyday simplicity of a basic ionization chamber in a household ceiling stands in sharp contrast to the necessity of high-purity solid-state detectors deployed across complex industrial containment zones. Aligning the correct physical detector with a precise understanding of the sievert scale forms the absolute, non-negotiable foundation of radiological safety.